Hello everyone. In this session, I am going to explain about the pump efficiencies which are used in the fluid power system. In the previous sessions, I have discussed about the different types of the pumps as well as their volumetric displacement and theoretical flow rates also we have discussed. But the efficiency we need to know. The efficiency means how much input power we are going to give, how much output power we are going to get from that system, how much input flow rate we are going to supply to the pump, and how much output from the pump we are going to get. Those efficiencies we are going to discuss in this session. Here, the first we'll take the what are meant by efficiencies and what are the different types of efficiencies. And these are particularly for the hydraulic pumps we are going to use. Those are used in the fluid power systems. The pump manufacturers run tests to determine performance data for their various types of pumps. The overall efficiency of a pump can be computed by comparing the hydraulic power output of the pump to the mechanical input power supplied by the prime mover. Here, overall efficiency will be the how much the hydraulic power output we are going to get for the particular mechanical input power. Okay, then that comparing this one, okay, that we are going to tell its overall efficiency. Then overall efficiency can be broken into two distinct components called volumetric efficiency and mechanical efficiency. These three efficiencies are discussed as follows in the further slides. First, we'll take that is volumetric efficiency that can be denoted as eta V. Here, volumetric efficiency indicates that the amount of leakage that takes place within the pump. This will be concerned to the leakage within the pump what is taking place. This involves considerations such as manufacturing tolerance and flexing of the pump casing under design pressure design pressure operating conditions. Okay, this is involved based on the consideration of that tolerances what are used for the leakage and flexing up a pump casing under the design pressure operating conditions. If the pressure increases, the leakage will be more, and if the tolerance will be more, then also the leakage will be more. Then the efficiency can be written as the efficiency eta V equal to actual flow rate produced by the pump to the theoretical flow rate pump should produce. The theoretically particular the flow rate will be set for the pump as per the design, and from that how much actually we are going to get from that pump. There is a Q actual by Q theoretical, and in this one the volumetric efficiencies typically run from 80% to 90% for gear pumps, 82 to 92% for vane pumps, and 90% to 98% for piston pumps. As from this, we can see that when the piston pumps are having the maximum efficiency. Note that when substituting efficiency values in the equations, decimal fraction values should be used instead of percentage values. For example, an efficiency value of 90% will be represented by a value of 0.9. During the calculation, this should be taken into here. 90% can be written during the calculation substituting in the equations. The next, second one, the mechanical efficiency that can be denoted as eta m. Then here the mechanical efficiency indicates the amount of energy loss that occur for reasons other than leakage. Here, amount of energy losses what are there? Other than the leakage, those are the friction losses. Then these friction losses what are there? How much power will be lost in the friction during the power transmission? That will be we have to discuss. This includes friction in bearings and between the other mating parts. It also includes energy losses due to fluid turbulence. the turbulence of the fluid, what is happening inside the pump, and due to that also what losses is taking place, that also considered. Mechanical efficiencies typically run from 90 to 95%. Okay, this for all the pumps. It may be gear, a vane, or a piston pumps. It may vary from the 90% to the 95%. The mechanical efficiency can be given as E time equal to pump output power assuming no leakage, actual power delivered to pump. Here, the leakage we are not considering, the leakage parameter we are not taking into consideration in this efficiency. That's why the pump output power assuming no leakage, that one. Okay, that by actual power delivered to the pump. Actual power, how much to the pump we have delivered. Here, pump power output, that will be in terms of the pressure and the theoretical flow rate. The pressure multiplied by the theoretical flow rate will be the pump output power. Output power, how much we are going to get from the pump. And input power in the form of, that is a torque for the particular speed of the pump we are going to supply, that is a theoretical torque. The theoretical torque means the whatever the losses due to the in this one prime mover only, that will not considered. Only the theoretically input torque we have to take multiplied with its speed of operation of the pump. Then here the P is pump discharge in Pascal, discharge pressure in Pascal or Newton per meter square. Qt is theoretical flow rate in terms of the meter cubes per second or a meter cube per minute. TA is actual torque delivered to pump in Newton meter. Actual torque, whatever delivered to the pump. The theoretical torque, whatever actually delivered to the pump. And N is pump speed in RPM. The M is pump speed in RPM. Then actual torque delivered we are going to take, and pump speed RPM we are going to take here. Then next one, here the mechanical efficiency whatever is there, that can also be computed in terms of the torques. How much torque we are going to produce from the pump or as output, and how much input torque is there, and in terms of the theoretical and actual torque we are going to take. The eta M can be written as theoretical torque required to operate pump and actual torque delivered by to the pump. This is the theoretical torque actual required to operate the pump, and this is the actual torque delivered to the pump by the prime mover. And in terms of this ratio also we can get the mechanical efficiency. Then note that theoretical torque required to operate a pump TFT is the torque that would be required if there were no leakage. That is, by assuming that there is no leakage, okay, by assuming that how much theoretical torque is required, that torque is required, that is called as a theoretical torque. Then equations for evaluating the theoretical torque and actual torque as follows. The theoretical torque is given by, here the theoretical torque will be in terms of the volumetric displacement multiplied with a P by 2 pi. Okay, this is the theoretical torque what is required to operate the pump. And actual torque is given by TA, actual power delivered to pump. Actual power, how much delivered to the pump is there, by N. Actual power, what we are going to deliver to the pump, that one, and N, its speed in RPM we have to take. That is the actual torque what is there, and by using these two torques we are going to find out the mechanical efficiency. Then further moving, third one, that is the overall efficiency, that is the eta naught. Then the overall efficiency considers all energy losses and hence is defined as follows. Here, the overall efficiency we are going to determine by considering all losses. It may be leakage loss, it may be turbulence loss, it may be friction loss. By considering all the losses, by means removing all the losses, what actually power we are going to get as the output. That is the actual power delivered by the pump to the actual power delivered to pump. Means here by the pump how much it will be producing the power, and to the pump how much we are going to supply the power from the prime mover. Okay, this is the input. Actual power delivered to pump is the input, and this is the output. Okay, that is the output to the input from the pump. The overall what we are going to get, that is the overall efficiency. Then the overall efficiency can also be represented mathematically as follows. That is, the eta naught can be determined by if know the mechanical and volumetric efficiency. The multiplication of the mechanical and volumetric efficiency will give the overall efficiency. If we determine the mechanical and volumetric efficiency, also we can find out the overall efficiency of the hydraulic pump. Then also the overall efficiency in this equation, eta m and eta v, the actual mechanical efficiency will be, that is QA by QT, Q actual by Q theoretical, and this eta v can be written as the volumetric efficiency P into QT by TA into En. Okay, this multiplied with this. Okay, this is the this first one is the volumetric efficiency, and this is the mechanical efficiency. Okay, that is a mechanical and volumetric efficiency. If you multiply, then we are going to get the this eta v and eta m from this. Okay, here after the multiplication, what we are going to get? That means here the QT we are going to get cancelled, and it becomes a Q into P by T into N. Overall efficiency it not can be written as P into QA by TA into N. That is the actual power delivered by the pump to the actual power delivered to pump. Okay, like this, the different efficiencies we have to calculate by using these equations, and I am going to use these equations while solving the numericals of these hydraulic systems. Thanks for watching. If you like, share, subscribe, and comment.